So I had to say that I really liked your seminar room, the one where I gave the talk. It felt like a nice theater. So
that was, yeah, I think you gave in
I think in the
Hall.
university. Yeah, somewhere.
It's in Morila. It's not computer science building, but yeah, we scheduled some of our talks there.
Oh.
Kuldeep, what's your preference for taking questions? If there are any, do you during the talk, or you prefer to wait till the end of the talk?
No, I would absolutely prefer questions during the talk.
So, okay.
Yeah, the only thing is I have only one screen. I think ideally one can just unmute themselves and ask questions.
Yeah, I'll keep track of the chat if anyone types a question on the chat.
Okay. Yeah, so maybe you might have to read it.
Yeah, I'll read it if that happens.
Yeah, yeah. I'll try to.
We'll give 1 more minute and then start. Yeah.
Sure.
Okay, I think we can start. So welcome everyone to the Computer Science Department Colloquium, as well as the TADS seminar, TADS for Theoretical and Applied Data Science seminar. Today, we are very happy to have Professor Kuldeep Meel from National University of Singapore giving a talk. Kuldeep received his PhD from Rice, and during his stay at Rice, he received 2018 Ralph Bird Award for Best PhD Thesis in Engineering. And actually, he received in 2014 Outstanding Master's Thesis Award from Vienna Center for Logic and Algorithms. So Kuldeep currently holds the NUS Presidential Young Professorship in School of Computing at National University of Singapore. He says his research interests lie at the intersection of formal methods and artificial intelligence, but I think it's much, much broader. His research interests span almost all of computer science, I would say. He is a recipient of 2019 NRF Fellowship for AI, and he was also named AI's 10 to watch by IEEE Intelligent Systems in 2020, and his work received numerous awards: 2021 Amazon Research Award, 2022 Sigma Research Highlight Award, and he also received Best Student Paper Awards at CP 2015, CAV 2020, and POTS 21. Okay. Okay, all yours, Kuldeep.
Oh, thank you, Pawan, for.
Before I just say, let me just say that if you have any questions during the talk, you can either unmute yourself or you can type in the chat. And thank you. Yeah, sorry. Go ahead, Kuldeep. Yeah.
Okay, good. Let's get started. Thanks a lot, Pawan, for having me. Since you reminded, it's been nearly 5 years. I gave a seminar at Iowa State, and you were also my host at that time. So. Good afternoon, everyone. So let's get started. I'm going to talk about next generation automated reasoning techniques that we have been designing in our group at NUS. And I'll start with a problem that most of us see sometime in our high school. So here is it. Given a Boolean expression, is there an assignment to the variables that make the expression equal to 1? So here's an expression that I want to point out. This expression is in a form that a lot of us are used to, which is called closal normal form or conjunctive normal form. In particular, you have brackets that are connected by and inside every parenthesis, you have variables or their negation. So if you stare at it long enough, I hope you will agree with me that assigning x1 and x2 and x3 to 1 would make this expression evaluate to true. Of course, as you can guess, we are not the first ones looking at this problem. In fact, the problem goes back at least 150 years ago. And here's Ernst Schroeder, who was one of the leading mathematicians and logicians in the late 19th century, went on to claim that in modern terms, one would say that finding the fastest algorithm would be the ultimate goal of mathematics and logic. Wow, that's quite a tall order. So as you can guess, there is going to be a twist in the story. Cook and Levin and the seminal work showed that the problem of set is NP-complete. NP is a class of problems for which we do not know a polynomial time algorithm yet. In many ways, one would think that's where the story would end in a tragic accident. But thankfully, the researchers in formal methods and artificial intelligence kept chipping at this problem. The earliest work started in late 1950s by Davis Putnam and then building by Logman and Loveland. And then through the late 1980s to 90s and 2000s. And all this work now we view as what is called set revolution. Don Knuth recently wrote an entire book on set solving, and I think he puts it very nicely to say that these solvers can now find solutions to problems that were regarded as hopelessly difficult just about a few years ago. So how did all of this take place? Well, the key ingredient behind the set revolution has been a really simple inference system, which is called resolution, which is to say that if you have two clauses that look like alpha or x and not x or beta, then if these clauses are true, then it must be the case that alpha or beta is going to be true. In mid-90s, João Marcos Silva and Karam Sakala at University of Michigan proposed a paradigm which is at the core of all the modern solvers. It's called conflict-driven closed learning. The high-level idea is that you try to guess an assignment to a subset of variables, and if that assignment falsifies the formula, then looking at the assignment that falsified the formula, you figure out what clauses you would like to resolve over. And you iteratively continue to do so. And then this is where very interesting observation that this seemingly simple system is sound and complete. So if you keep applying it, you will eventually be able to figure out whether formula is satisfiable or not. So building on this paradigm, in last 25 years or so, the communities at the intersection of formal methods and artificial intelligence have been hammering and working really hard to build scalable solvers. Just to show you the progress, here are all, there's a competition, and most of the progress happens by focusing on the competition. In this case, it's called set competition. And here are all the solvers that have been the winning solvers in the competition. On y-axis, we have the number of instances solved. On x-axis, we have the time taken. All these solvers are run on standard suite of benchmarks on the same hardware in 2020. So what it means is that a point here indicates that the corresponding solver could solve about 20 problems, each of them in less than 3,000 seconds. In 2002, the best set solver could solve 50 problems. Today's the winning solver is able to solve almost 250 problems. So there's a 5-factor improvement in the ability of these solvers to be able to solve these problems. And this has been at the core of what has propelled the SAT revolution. And that made the SAT from an academic problem to an industrial problem with a lot of impact. As I speak, the solvers are used in wide variety of applications such as hardware and software verification, security, planning, and so on, by companies ranging from consultancy services companies to Bitcoin, to Amazon Web Services to make sure your data is not leaking or information is secure when you are running your computation on Amazon Cloud. And at this point, we ask question that, well, now that SAT is easy, and this was mid-2010s, we asked that if SAT is easy, it is time to look beyond satisfiability. The question was not just purely from academic viewpoint, it's also rooted in the motivation that for a lot of problems where because the systems have grown on to be more complicated and now we care about different kind of properties. So a lot of problems nowadays arise that cannot be formulated into a SAT problem, such as the problems like quantifying the information leakage, quantifying how often the systems are robust, or when you put these systems into critical infrastructure, you want to quantify the resilience of these systems. So not that SAT is a problem about yes or no. It's a qualitative answer. And there are a lot of questions that arise as we have grown into an interconnected society that focus on the quantitative nature. So what kind of problems I'm talking about beyond satisfiability? Well, I'm talking about being able to quantify the behavior, being able to sample representative behavior, and if we succeed, then being able to design systems that are correct by construction. The low-level key technical problems that we focus on are counting, sampling, and synthesis of systems. Why should we focus on these problems? Well, these problems are very fundamental and as a result have application in wide variety of areas of computer science, ranging from reliability of networks to hardware validation to interpretable rule learning. In the interest of the time today, I'm going to just focus on the problem of counting and the associated applications to showcase the progress that we have made over past few years. And we have been following the similar recipe for other problems in the context of sampling and synthesis. So let me define the problem of counting more formally. We have a set of constraints over variables. I'm going to use the notation sol of f to indicate the set of solutions of this formula. The problem of SAT was to determine if the set of solutions is empty or non-empty. Now we can talk about the properties of this set. In particular, the problem of counting is to determine how many solutions are there. You can have a weight function over the assignment space. And in that case, the weight of a formula becomes sum of the weight of the solutions of this formula. And now the problem of counting becomes to determine the weight of this formula. Let me give a quick example to make sure we are on the same page. Here's a simple formula, x1 or x2. The weight function assigns weight of 1/6 to assignment 0, 0, and 1, 1, and weight of 1/3 to rest of the two assignments. The set of solutions of this formula are essentially all the assignments to x1 and x2 except 0, 0. So the problem of counting is to be able to estimate the weight of this formula, which is nothing but the sum of the weight of each of these three satisfying assignments. So the answer should be 5/6. Okay, this would be a good point if there are any questions about the basic definition of the problem.
So,
right.
So why do you? So what is the necessity to take the weight here? I didn't fully understand.
Well, yeah, I mean, you can define a weight function in its full general form. So this is problem that I'm defining in its full generality, where you can say that I don't give equal weightage to all the solutions. So some of the solutions I would like to give higher weight.
Yeah, makes sense.
Okay. So at this point, one immediate question is, well, where are the applications of counting? So I'm going to talk about 3 applications today. The applications from resilience of infrastructure networks to application security, and then in the AI systems. I'm going to show how all these 3 applications reduce to counting. And then in the second half of the talk, I'm going to focus on how we went about designing algorithms. And the important viewpoint that I want to get across is our philosophy of designing algorithms that go beyond worst case analysis. And then these algorithms are designed in a tight coupling with underlying systems whose design is influenced by data-driven algorithmic engineering. So let me start with the first application. This is what we started working with civil engineers at Rice University. Here is Rice is located in Houston, and here's the city of Houston, which looks beautiful at night. But if you have been following news in past few years, city of Houston is prone to hurricanes, and these hurricanes cause havoc and require city authorities to conduct operations that are resource intensive. In such times, it is important for city authorities to have access to tools and techniques that can reliably predict the effect of these natural disasters. We focus on the problem of being able to predict which parts of the city will have blackout. Let me put the problem more in computer science terms. Here's a power grid of one of the cities in US. We can treat this power grid as a graph. There are nodes that generate power. Let's call them S. And let's say we are interested in particular node T. To model the effect of natural disasters, we can assign the failure probability to edges. And now we can compute the question of interest is, what is the probability the node gets disconnected from this, all the sources? How do we go about solving the problem? Well, at every point in the time, we can denote the configuration of network by a vector of size E, such that the weight of this configuration is same as the probability of observing the configuration. This vector, essentially what it indicates, it's a 0, 1 vector for each of the edges. So when an edge is, when the value of the corresponding bit is 0, then it implies that the edge is, in case of hurricane, gotten disconnected, or if it is 1, then it implies that the edge is still intact. We are interested in all the configurations where T is disconnected from S. You can represent the set of all these configurations implicitly as a solution to a set of constraints over the edge variables. And once we have these constraints, then the problem of computing a probability of T being disconnected from S is essentially sum over all the configurations weighted by their probability. So this is precisely the problem of constraint counting that I defined. You have a set of constraints, you have a weight function over the assignment space, you want to sum up over the weight of all the solutions to this set of constraints. Let me now discuss a problem that comes from very different area in security. So here are 2 very simple toy programs. What these programs are supposed to do is that they have some secret password that they are working with, and there is some user input. These programs have to check whether the user input matches the secret password or not. If the answer, if it matches, it should return answer yes, otherwise no. However, you will notice that the program on left is something that one would write very naturally. All you can do is that at every, you go through the entire array, and at every point you check if the secret password matches the user input. And the moment you see there's a mismatch, you return no, otherwise you return yes. The program on the right looks a little bit complicated. It's trying to have some variable match, and it keeps updating this variable match, and finally it returns the answer yes or no. One might ask, why write such a complicated program? Well, the reason you might want to write such a complicated program is because there might be an adversary which might be looking at how long a program takes and try to use that to infer something about the secret password we have. In particular, if you look at the program on the left-hand side, you can see that the adversary can guess if the first bit matches or not based on how long it takes, because the program on the left would immediately return and the first bit would not match. So how do we characterize how much information is leaking? Well, we rely on the classical notion of Shannon entropy, where we would like to be able to understand what is the probability a program takes k unit of time, and then we use the standard formula for entropy computation. How do we compute each of these probabilities? The idea in the field is to encode programs symbolically. In particular, you could say that I want to encode a program, let's say, with a formula phi, and so that the probability that program takes k units of time can be rewritten as sum of the weight of solutions of this formula weighted by the probability of adversary trying out the input. So again, the problem of computing entropy reduces to the problem of counting a set of constraints, a weight function over these constraints, and you are interested in computing the sum of the weight of these solutions.
So, Kuldeep, just a question.
Yeah.
So when you say here, the solutions of this constraint, what does it mean when we have a program here?
Yeah, so the solutions of these constraints are essentially all the inputs for which the program is going to take k units of time.
Oh, okay. I see. Thank you. Yeah.
Now let me discuss yet another application to emphasize how general the problem of counting is. And this is comes from our work in the context of modern machine learning systems. And one of the observation that has been consistent in the community is that the systems are shown to be brittle to small perturbations. So an important question now becomes is that, well, how do you quantify the robustness of these systems? So more formally, what we are interested in is to be able to sum up over all the probability of all the inputs. And in particular, we are interested in the inputs where if you make a small perturbation, you give a different output. We can again formulate this into counting. Now you know the recipe. We are going to have a formula which indicates all the inputs so that for a small perturbation, you get a different output. And again, we are going to sum over the weight of all these configurations, which is the probability of the particular input over the set of solutions of these constraints. Similarly, you can again apply the same recipe to look at the problem of quantifying how fair a system is. And again, the problem that one is interested in is computing over the space of all the inputs, where if you change, let's say in this case, if you change the race of a person, the network gets a different output. So you are again summing up over the probability of all such inputs, and the problem again reduces to that of counting. So I hope at this point I have shown you that the problem of counting is very natural, arises in lots of different domains. So now let me discuss how we went about designing the techniques for counting. And as you can expect, if a problem is so natural, there is certainly a lot of work in the past. In particular, the problem of counting the study was first initiated by Leslie Valent in some seminal work that showed that problem is sharply complete. And since then, there has been a lot of work that falls in broadly into two spectrums. This was this snapshot of all the work when we started looking at this problem in mid-2010s. So in particular, you have techniques that can scale to large instances, but fail to provide guarantees over the estimate they are computing. On the other hand, you have techniques that have rigorous guarantees over estimates they are computing, but often fail to scale to large instances.
I'm just attending this one.
Our focus here has been to design techniques that have rigorous guarantees and are being able to scale to large instances. The techniques that we have designed provide what are called epsilon delta or probably approximately correct guarantees. In particular, the algorithm takes a formula, the weight function, and two parameters epsilon and delta, and it ensures that the estimate it is computing is within 1 plus epsilon factor with confidence at least 1 minus delta. So as a first step, we could show that you start with the formula and the weight function. It is possible to reduce into another formula f prime, so that the weight of this formula can be just simply written as a constant that depends on W times the number of solutions of this formula f prime. And the key idea is that you can encode again weight function as a set of constraints. Of course, there's a caveat here, which is that the size of this f prime will depend on the representation of your weight function. But we showed that for most of the natural weight functions, the size blow up is not very large. And so the problem that we had to now solve is to determine how many solutions a formula has. So let me jump right into the core of the techniques that we have been developing. And in order to do that, I'm probably start with a problem that may be more closer to home. So suppose you want to count how many people in Ames like coffee. So how would you go about? If my search on Wikipedia this morning is correct, then the population of Ames is 66,000. You can assign every person, let's say, 17-bit identifier so that you are able to cover all the people. So how would you go about figuring out how many people in Ames like coffee? Well, we can maybe pick about 50 people and count how many of them like coffee and scale the count. Is this going to work always? Probably not. Because what if there are only 5 people who like coffee? So it is unlikely that you are going to find anybody who likes coffee. Or if you find somebody who likes coffee, then your estimate will be in tens of thousands. So this is where we want to rely on the power of the set solvers. In particular, the set query here is to ask, find me a person who likes coffee. And the solver can answer questions like, find me a person who likes coffee and the person not person Y. So if there are only 5 people who like coffee, here's a simple algorithm. Find me a person who likes, you ask for the first person, then you ask for the second person and so on. You make 5 queries and you are done. The solvers are incredibly powerful, so we should be able to do in 5 queries. Is this going to work always? You can see where this is going. What if everybody likes coffee? You'll end up making exponentially many queries. Exponential in n, which is the number of bits to represent the problem. So a key question here is that can we do with lesser number of set queries? Probably linear or logarithmic in n. So now I'm going to jump into the core of techniques that we have been developing, where let us look at the blue circle as the space of all possible assignments, and the dots represent satisfying assignments. We have powerful solvers that can allow us to enumerate solutions. But if the solutions are too many, then such an enumeration would not work. So what if we could partition the space of solutions into cells that are roughly equal and small enough so that we can go and pick a cell randomly? And then if the cells are small enough, then you can use the solver to be able to enumerate all the solutions, and our estimate will be the total number of solutions in this randomly picked cell multiplied by the number of cells. The immediate challenge that comes to mind is, well, how are we going to partition into roughly equal small cells without knowing the distribution of solutions? And another challenge, which is subtle but equally critical, is how many cells should we partition into? So let me discuss how we went about addressing the first challenge, which is that we are interested in designing functions that maps assignments to cells. In classical computer science terms, these are called hash functions. Once we have such a hash function, we can represent the solution in cell alpha as the conjunction of the solutions of the formula intersected with all the assignment that H is mapping to alpha. You can see that a deterministic hash function is unlikely to work And so this is why we rely on the power of randomness. In particular, we rely on the notion of two-wise independent hash functions, which was proposed by Carter and Wegman in 1977. So what does two-wise independent hash functions allow us? Well, let me define this class a little bit formally to be able to argue about them. So two-wise independent hash functions, let's say over the assignment space over n variables to cells that can be represented by m bits, ensure that if you pick any pair of assignments and any pair of solutions, then and if you pick a hash function randomly, then they ensure that the probability H is mapping y1 to alpha 1 is same as probability H is mapping y2 to alpha 2, which is 1 over the number of cells. Furthermore, these events are pairwise independent. In particular, the probabilities are just the product of margin. Having access to two-wise independence ensures that the random variable of our interest, which is the number of solutions in a randomly chosen cell, the expectation of this random variable is essentially the total number of solutions divided by total number of cells. Furthermore, the variance is small. In particular, the ratio of variance over expectation can be upper bounded by 1. How do we construct these functions? Well, I'm going to tell you the standard construction. So you can, we have a set of variables, x1 to xn, to construct a hash function that maps assignment space to cells with m bits. We choose m random XORs. How do we choose every XOR? We pick every variable with probability half and we XOR them together. So the expected size of each XOR would be n over 2. To choose a cell randomly, we set each of these XORs to 0 or 1 randomly. And now the solutions in a cell are really the conjunction of the original formula and all these Q1 to QM XORs we have constructed. And this is where you can rely on the power of set solvers, and you can call a set solver to be able to enumerate solutions. The second challenge was, how many cells should we partition into? To show how to go about it, a little bit of a small technical detail, which is that what do we exactly mean by a cell to be small? So we say a cell is small if it is about threshold many solutions. This inversely depends on epsilon. So we want to partition into the number of cells so that all the cells have about threshold many solutions. So the right number would be total number of solutions over threshold. Of course, we don't know the number of solutions. So how do we get around? Well, we can do a linear search over the number of cells. So in particular, let me put it graphically. You start with the formula and you ask the question, is the number of solutions less than or equal to threshold? If the answer is no, you partition into 2 cells, which is by putting 1 XOR constraint. And you pick one of the cell randomly. You ask the question again. If the answer is still no, you partition into 4 cells and pick one of them randomly. And this is by just adding another XOR constraint. The answer is still no. You keep adding more and more XOR constraints until you reach a point where the number of solutions is indeed less than or equal to threshold. And at that point, our estimate is the number of solutions in this cell multiplied by the total number of cells. Of course, you would be quick to observe that we don't have to really do this search linearly. We can indeed do a logarithmic search. Okay, so the idea was we would like to be able to partition. We use these 2-wise independent hash functions that are based on XORs, and then we can do a logarithmic search. So does all of this work? Does it give the kind of guarantees we are looking for? And the answer is yes. It ensures that the algorithm I just presented takes 2 parameters epsilon and delta, and the estimate it gives is within 1 plus epsilon factor with confidence at least 1 minus delta. Furthermore, the algorithm makes only logarithmically many calls to set oracle. So this is the framework that we proposed in our CP 2013 paper, which in 2018 was recognized as one of the 25 papers. So, well, All of this was 2016, the problem solved. To measure the progress, we went back to the philosophy that has fueled the SET revolution, which is that you want to construct a large set of benchmarks and want to be able to measure how good these tools work. So we took about 1900 benchmarks and we tried to analyze how well the solver works. So these were the early years of designing this framework. And as you can see, again, the plot here indicates that the tool could solve about 400 benchmarks, each of them in less than 1,000 seconds. So we have about 1900 benchmarks. At that point, the best we could solve was about 500 benchmarks. So the answer is yes and no. We could solve quite a few benchmarks, but we're still far away from what we wanted to set out to achieve. So at this point, some of you might have a little bit of a deja vu, because 5 years ago, I came to Iowa State and I presented exactly this. This is what I talked about. But I did promise something. I told you that we are just starting out. And what I promised, here is a slide from the seminar, to promise that we are going to work and try to build these counters and samplers and achieve the speed up that I promised at that time. And I said that this is going to require ideas from theory, statistics, and systems. So now let me try to report how much we have made progress ever since those 5 years ago. Well, the tool today is able to solve nearly 1600 benchmarks. In particular, what I want to highlight that we are able to solve almost 900 benchmarks, each of them in less than 1 second, in comparison to where we could solve about 500 benchmarks in each of them in 5,000 seconds. So today we can solve in less than 1 second what we could solve in 5,000 seconds about 5 years ago. So how did we get there? I'll again quote Byron Cook at Amazon Web Services, which is that having access to a lot of diverse set of applications requires a lot of investment in these tools, and then hopefully it also creates a virtuous cycle where we get more and more interesting applications. In particular, to achieve this scalability, and which is true mostly whenever you want to build a scalable tool, is that you have to fit lots of pieces of puzzle together. Yeah, we had to work on designing new theoretical constructs, algorithmic insights, and system building. In the interest of the time, I'm going to show about 3 things that we did to give a flavor of different work that has gone on to build these tools to be scalable. So let's go back to the primary challenge we were dealing with. The core of this framework is to be able to partition into small, roughly equal small cells, and we relied on these XOR-based hash functions. So in particular, we said that we are going to construct these M XORs, and then we are going to call a solver, which has to deal with conjunction of this formula and these M XORs. I mentioned that we should be able to use state-of-art solvers to be able to handle these queries, but turns out, remember, these solvers are not oracles. Their performance depends on the kind of formulas you give to them. This is why when I mentioned the set is easy, easy was qualified with quotes. And in our particular case, we need to be able to handle formulas that are conjunction of the original formula, which is represented in conjunctive normal form, and these random XORs. So these are the formulas we call as CNF XOR formulas. How do we go about handling the CNF XOR formulas? As I mentioned, the state-of-art solvers are based on repeated application of resolution. But resolution and XORs don't gel with each other very well. In particular, we know there are exponential lower bounds for resolution to solve random XORs. However, random XORs are not something to be feared of. We know a very simple polynomial time procedure that we learn in our high school. It's called Gauss-Jordan elimination. But we are interested in solving the formula that is conjunction of both CNF and XOR. So you can't independently solve them and hope that you are going to find the same solution. So how do we go about solving them concurrently? Well, we have to be able to solve both the CNF and Gauss-Jordan elimination in incremental manner. What do I mean by that? On one end, the CDCL is going to make certain decisions and then is going to tell the Gauss-Jordan elimination that, hey, I have made these decisions. What do you think? The Gauss-Jordan part is going to say, well, based on what you have made decisions so far, I can deduce that certain variables should get certain values, or the decisions you have made so far give me a conflict. And it can do this reasoning by applying Gauss-Jordan elimination. And you have to keep going on and on and on. Remember, we are dealing with formulas involving hundreds of thousands of variables. So we are invariably going to have millions of such calls to each of the solvers. And of course, to be able to design something in that works well in practice, a lot of work that has gone on in designing efficient data structures that can allow such propagation and analysis of conflicts. And furthermore, we realize that since these formulas have a lot of interesting structure of relying on random XORs, so we could design heuristics based on using the progress in machine learning, where you look at the stress of the solver and you apply supervised machine learning to be able to learn new heuristics. So that's number one thing, which is that in order to be able to handle these formulas, we have to design new solvers that can handle this efficiently. Now let's go back, and again we have the same question. Can we do better? And in order to that, the observation is, well, we were constructing these hash functions and we were picking every variable with probability half. Now the thing is that, do we have to really pick every variable with probability half? Why so? Why are we asking the question? Well, it turns out, as I mentioned again, we have been able to design solvers that can handle this formula as well, but these solvers are not oracles. In particular, again, their performance depends on the kind of formula. And in this case, we saw that the solver's performance degrades with increase in the size of the XORs. So one thing that one wants to do is that, can we construct smaller size XORs? The question is that, do we have to really pick every variable with probability half? Does every variable really matter in a formula? Perhaps not really. So the key observation here is that we don't really require every variable to specify a solution space of a formula. So look at this formula, x3 if and only if x1 or x2. Here, x1, once I give an assignment to x1 and x2, you can determine the assignment to rest of the variables. So you can formulate this notion into the notion of independent support, which is to say that a subset of variables is independent support if for every pair of solutions, if two solutions agree on independent support, then they must be equal. Why does this help? Well, we have to put XORs only over independent support. Is this going to really work in practice? Turns out yes, because remember, we started with problems at high level and we reduced them into formulas. And during this process of writing them into formulas, we had to introduce lots of extra variables, which are called auxiliary variables. And all those variables that we introduced are dependent. So important question was that, well, since we are going to have to work with these formulas, is there an algorithmic process there that can help us determine the independent support. We had identified this challenge in 2016 and we designed the approach that would make logarithmically many calls to a SAT solver. But to our surprise, it took a lot of time in order to even just determine the independent support, that it was not worth it. So then last year we went back and tried to figure out what's going on. Why is it taking so much time? Of course, the conclusion was fairly straightforward. These calls are really hard for the solver. So then we designed another approach where we make linear number of calls, but now the calls that we make are easy for the solver. So, and this is where the new approach leads to about 2 orders of magnitude runtime improvement when you combine it with the rest of the counting procedure. So here, the design of algorithms is heavily influenced by this observation that the solvers you have are not same as the oracles. Their performance depends on the kind of formulas you give to them. Now let's go back to the next phase that I want to discuss is that again, look at how we constructed these XORs. And the question is that do we have to really pick every variable with probability half? And now I want to emphasize on the fact about probability half. So why does it matter? Because see, if we could pick variables with probability less than half, then the XORs that we are going to have are going to be smaller. So here are some quick facts. If we pick with probability less than half, there are no guarantees of two-wise independence. And if, remember, we use two-wise independence to imply that the ratio of variance over expectation is low. But our starting point was the observation that the two-wise independence implies that variance is low. Well, it doesn't mean that you really need two-wise independence to make this conclusion. So we went ahead and tried to navigate, investigate this further. And it's quickly, one can determine that if you pick every variable with probability P, then the ratio of variance over expectation is upper bounded by 1 plus this Pesky looking factor, which is essentially this expression depends on all the pairs of solutions where W is the distance between these solutions. And the important observation here is that if the value of P is half, then all of this evaluates to 0. And this is what the pairwise independence gives us. There have been earlier attempts, because we are certainly not the first ones to investigate that can we pick with variable with probability less than half. The earlier attempts essentially did not yield much progress because the way they tried to proceed with was to rewrite this expression by saying that let us go over all the solutions of a formula and then try to ask how many solutions are at distance W. And the distance we are talking about is the Hamming distance. So you can say that the number of solutions at the Hamming distance W are n choose W. But turns out that n choose W grows very fast with n. So one could not upper bound the variance over expectation. So something that really helped us is to able to rewrite this expression into another expression here, where we are writing as the CF of W. What is CF of W? This asks that how many pairs of solutions are at distance W. So we are rewriting this expression into saying that expression can be the number of solutions at distance W times R of WM. The interesting part is that CF of W, computing CF of W can be done by relying on the power of isoparametric inequalities. So the study of isoparametric inequalities are to look at the Boolean hypercube and ask how many points of the hypercube are at certain distance. So what all of this gives us is that we were able to show that it suffices to pick the mth XOR that we are picking with probability log m by m. So we get a logarithmic from linear in m, we are now able to construct XORs that are logarithmic in m. So as I discussed, I showcased three parts of the puzzle that we try to fill in, that requires us to design more algorithmic advances, system design, and new concepts. So where does all of this lead us? Well, the framework that we have designed all these years is highly generalizable. In particular, one is able to look at the context, such as you can look at in the streaming fashion.
Go above and beyond.
Where you can say that I want to compute the union of sets in a stream, and this is a fundamental problem in databases where you are interested in counting how many unique elements you see in a stream. If you are looking at our coffee example, you might be asking how many unique customers visit coffee shop. You can also just go beyond counting satisfying assignments. You can say that if I have an unsatisfiable formula, I would like to count how many minimal number of subsets of clauses that I have that are unsatisfiable. And in fact, you can go beyond the formula that are in CNF. If the formula is originally expressed in the DNF, then the algorithm that I just discussed gives us a fully polynomial randomized approximation scheme. So does this work in practice? I'm going to showcase by one example, which is in the context of reliability of networks. So here we took one of the cities and we labeled all the terminal nodes. Since this is a well-studied problem in the past, there has been a lot of work, and here is the state-of-art tool from civil engineering that relies on recursive decomposition of graphs. How does it work? Well, it times out on all such instances. The tool that I discussed, ApproxMC, is able to consistently give an answer in under 150 seconds. So to cap off, all these advances has allowed us to design the techniques that can handle now a large, significantly more benchmarks at significantly high runtime performance. And in some sense, we are able to now beginning to see the virtuous cycle where if you build a technique that can scale to large instances, then you begin to see more and more applications. So in particular, the tool is open source. Now we are seeing applications by other researchers in contexts such as bioinformatics, in computer networks, and so on. And some of the exciting development has been that there's a new conference and the competitions that are being organized for counting. And one of the things that I am very happy to see is that there has been a lot of work in development of tools across the globe with participants from different cities across the globe. So I discussed one such application of counting. Of course, we have been working on other problems such as sampling and synthesis. So where do we go from here? Well, I think we are getting close to the beyond set revolution that I promised about 5 years ago. In particular, to be able to achieve this revolution, we need to work along the technical directions that would require us to pursue tighter integration between solvers and algorithms, to be able to design heuristics that are data driven and build on hardware accelerators. Every such revolution requires challenge problems. So here are 3 challenge problems that we hope to be able to achieve. In particular, being able to design verify neural networks with about 1 million neurons, being able to handle power grids of the size of Los Angeles, and being able to handle programs with about 10,000 lines of code. And beyond that, if you look at what we have done so far, is to look at the problem of set solving and look at richer queries such as counting, sampling, and synthesis. The community in formal methods and artificial intelligence have also looked into looking at more expressiveness, in particular satisfiability modular theory. So where you are looking at theories such as bit vectors, linear integer arithmetic, strings, and so on. So at this point, I think the time is ripe to start working on beyond SMT techniques. where you want to ask similar questions in the context of SMT. So in the counting there would become integration, sampling, and synthesis in being able to handle theories that are much richer than propositional logic. So with that, I would like to conclude. Thanks for being a wonderful audience this afternoon. I'll be happy to take any questions.
Thanks a lot, Kuldeep. It's a very interesting talk. If we have time for questions, you can either type in the chat or unmute and ask. Okay, maybe let me start. Just one. When you talk about the Gaussian elimination to do with the XRs, typically Gaussian elimination is also expensive, like cubic time. So how do you make it scalable?
Yeah, that's very good question. So in particular, there are two things. One is that you want to be able to do incremental Gaussian elimination. In the sense you had a set of XORs, and at every point you assign a subset of the variables, and now you want to be able to apply the Gaussian elimination for under this partial assignment. So the way to implement this, because the incrementality is the most important part, since you are going to be calling this few millions of time in a formula. So you implement using this simplex style data structures. So you have these basic variables and non-basic variables in order to see that. So you initially make the matrix into row echelon form, but then at every point you have these basic and non-basic variables, and then you keep updating them. So yeah, the correct implementation requires incrementality, and that requires you to be able to quickly guess whether some row needs to be updated or not. So you so that's kind of what is really required to make it work in practice.
So any questions? Okay, if not, I have one final question. So it's for all the progress that you made, you need a fair bit of mix of theory and systems building and implementation. So if you just ask, what do you think is the most important or most challenging?
Well, I guess I think in order to make this tool scalable, you do need all of the three. In particular, the theory that one needs to build on is being aware of these solvers not behaving as oracles. So you want to be able to prove for the algorithms where you had to make certain kind of queries, because that's what the solvers can afford well. So it requires a slightly different aptitude towards having these queries. Yeah, and I mean, set solving is really the story of doing good software engineering with applying beautiful theories. So if we don't, I think engineering part is equally important, in the sense that there's a huge improvement that you get by making sure you have the right data structures, right analysis. So I think, yeah, it's a tricky question. I mean, it requires both the communities, both in the engineering, to be aware that you can't do certain things because they won't be supported by theory, and in theory to be aware that you are constrained by what kind of algorithms you can design based on the behavior of the solvers.
Okay, thank you. Okay. Thanks a lot, Kuldeep, for a very nice and engaging talk.
Yeah.
Thank you all for joining. Yep.
Bye.
And if any of you would like to stay a little bit longer, I'm guessing Kuldeep would be available if you want to talk.
Yeah, certainly. I'd be happy to discuss.
Wait for a few more minutes.